there's the title again. Is that in focus? Everybody can hear me? So so let me begin with just a little bit of background, a couple references. So starting in 1988, coming out in 89, Witten solved the quantum field theory, a fairly famous solution based on the classical action from this now very famous paper of Chern-simons, 1968, which, as we'll see here, have been used for all sorts of purposes, these invariants. And in this case, the solution to the quantum field theory gave new invariants of length in 3-manifold. And there was also another approach that came out at the same time using quantum groups of Reshetikhin and Tureyev. So Atiyah elucidated the properties, some of the properties of the quantum theory that Witten constructed when he gave axioms for topological quantum field theory. And these are analogous to axioms Siegel developed for conformal field theories. Okay. So around that time, while these things were in their air, Digraph and Witten and Ramadas, Singer, Weitzman had some papers discussing the properties of the classical action. And in my PhD thesis, actually, back in 91, I gave the complete structure, or at least what I claim, of the classical theory satisfying the classical analogs of the topological quantum field theory axioms. So that's what I'm going to talk about today. I'm going to explain how the Chern-simons invariants really give you this classical theory. And I'll explain the axiomatic structures. And the construction will use some, the full-blown construction will use some equivariant version of differential characters. And differential characters were introduced by Chigurh-Simons in 1985 and gave a nice sort of homological algebra machinery within which to see various invariants in the Chern-Simons invariants. So in my thesis, and I won't talk about it more, but just as an example of application, I use this classical construction, which comes equipped with an action of the diffeomorphism group of Riemann surfaces on a line bundle to construct the quantum Hilbert space of Chern-Simons theory, which is one of the ansatz ingredients used in Witten's solution. And that was in a paper with Della Pietra and Witten. So I'll talk about the generalized gauge Wess-Zumino action, but I'll refrain, for lack of time, and hopefully others at the conference will talk about some of these things, from giving applications, relationship to anomalies in index theory, although these classical theories really do often come from index theory, recent stringy conformal field theory sort of applications. So I could give a lot of more references, but just to be succinct, I think maybe the most relevant in the spirit of what I'm talking about is maybe papers by Fried coming out in 92 and later, and including recently, to try to talk about some of these stringy actions. Okay, so the spirit of this talk is to sort of give you some of the properties that physicists use of the theories right when they start with the classical theory. So going back to the beginning, starting with things, let me just remind you about Lagrangian mechanics for a minute. So in the simplest example, let's let x be a real-valued function of time. And I will define an action. This means a function of this path x to just be the integral over time of a mass over 2 x dot squared minus a potential function of x. So in looking at variational principles, physicists look at the variation of the action s under a variation delta x of the path x. So this is just a directional derivative on this infinite dimensional space of paths. And, well, so if you vary delta x, you can see you'll have a delta x dot here and a delta x here. And we can integrate by parts to get the time derivative off the delta x. And so when we integrate by parts, we can write this variation as a piece which is an integral over time, where the integrand is just given by this object. Setting this equal to 0 is the so-called equation of motion. This is just Newton's equation, setting that to 0. And then we get also a boundary term because we did the integration by parts. And this boundary term is just mx dot delta x going from t0 to t1, which we can think of as a function of some data at the boundary. I'll call pi of x data at the boundary. So pi of x is the initial position in velocity and the final position in velocity. So this only depends on that boundary data. Some of you might also recognize it in this form, where p is the momentum. So, okay, so that's a fairly basic starting point. But I write it this way because it generalizes directly to Lagrangian field theory. So now I'm going to let F be the space of fields. So we've got some manifold with boundary. The space of fields is some section of some bundle over that. And I'm supposed to be given a classical action. It's a function on this space of fields, which has the form that S of phi is the integral over the manifold of some Lagrangian, what's called a Lagrangian density. And this is supposed to depend at each point in the manifold only on the field and finitely many derivatives at that point. So then we can just do the same trick. We can look at the variation of S in the direction delta phi, integrating by parts. There's a bulk piece that doesn't use any of the derivatives of delta phi because we used integration by parts or Stokes' theorem to get rid of them. And then there's a boundary piece. So this equation delta S delta phi equals 0 is, again, the equation of motion. It's just the thing that pairs with delta phi when you integrate over m for the bulk term. And then we get this boundary term, which is an integral over the boundary, as before, of some local density W. And this projection map is a map from the space of fields to the space of what I'm going to kind of loosely call Cauchy data or boundary data at the boundary. And we want to include enough data in this Cauchy data, enough of the fields and their normal derivatives at the boundary so that theta only depends on pi of phi, pi delta phi. So in fact, it's just a one form on A. So it might not seem natural to do the following if we're just thinking in terms of classical mechanics. But for the generalization, it is natural to introduce the trivial Hermitian line bundle over the space A. And we can introduce a connection on that trivial bundle, which is just which has connection one form theta. This is the trivial connection on the trivial bundle. And then I will introduce what I'm going to call the generalized action, which is just e to the I times the ordinary action. And I'm going to view this as a section of the pullback of the line bundle over here to F. Of course, the line bundle right now is trivial, so it doesn't mean anything to do that. It's just a complex valued function. But in the sequel, this will be non-trivial. So now if I look at the covariant derivative of the action using the pulled back connection on this bundle, then the boundary term here cancels, right? It exactly is canceled by using the connection one form. And we find that the covariant derivative is just this bulk integral over the, physicists would say maybe the space-time manifold M. Okay? So, so that's going to be my motivation for 4 pages of axioms. Sorry. You know, for purposes of time, I can't elaborate with the hundreds of examples. But I think this is a fair characterization of the properties, at least of many of the theories that physicists are interested in when they want to quantize in a sort of geometric setting. Okay, so let me let B be just some category of compact-oriented manifolds with additional data. So in the case of Chern-Simons theory, I'm going to think of the category of manifolds equipped with the principal bundle. And those manifolds then have diffeomorphism of such a manifold as an automorphism of the principal bundle. You can take disjoint union of such manifolds. You can do orientation reversal and so forth. So I could state the axioms I want this category to have. What's that? Generalized Lagrangian field theory. Okay, so now I'm going to just define a d+1 dimensional generalized Lagrangian field theory on this category of manifolds I've picked. It's a collection of a whole bunch of data. Okay, so what is the data? So if we're given a closed d-dimensional manifold, so I'm going to take all the d-dimensional manifolds to be closed. A lot of people talk about the axioms you want to extend if you want to allow these to have boundaries. But for now, let me just take these to be closed. Then we should be given this space of Cauchy data for this space manifold with a line bundle over it. Just as before, it's a Hermitian line bundle with connection. So that's the axiom that we're supposed to be given that. And then for a d+1 dimensional manifold, what we're supposed to have is a space of fields, a map to the boundary data, and then a norm 1 section of the pullback line bundle. So this is just what we had in the example of Lagrangian field theory. Okay. So this data should satisfy a bunch of properties. So first of all, it should be functorial in the sense that the diffeomorphisms of this B manifold, for example, automorphisms of the principal bundle, should act by symmetries of the data in 1, if this is a D manifold, or if the diffeomorphisms of a d+1 manifold should act by symmetries of the data in 2. Okay? Any questions? So, and these are just the analogs of Atiyah's axiom so far. What I stated so far, in fact, is I added base spaces F and A in Atiyah's axioms, if you know them, and I added the connection, and I made the line bundle to be a line bundle instead of a vector space. But these are all really direct analogs of the Atiyah axioms. So involutivity is that these were always compact-oriented manifolds with additional structure, and these spaces shouldn't depend on the orientation. That the line bundle depends on the orientation in that if you take the opposite orientation of sigma, that's what I denote by this check, then the line bundle goes to the dual line bundle, which, because it's a Hermitian line bundle, is the same as the complex conjugate bundle. And similarly, the action for the manifold with reversed orientation is just the dual or complex conjugate action. Remember that the action here belongs to the line bundle associated with the boundary at the point pi phi. But then here it's supposed to be the boundary with opposite orientation. So that's why we have the dual. Okay, so multiplicativity is just the statement that the space of Cauchy data and fields just takes disjoint union to cross product, and that for line bundles, disjoint union goes to tensor product of line bundles, and same for the action. If we have a field on this disjoint union, that's just a pair of a field on M1 and a field on M2, and its value should be in the tensor product of these two, which belongs to the right space because of this axiom. Okay, so the next axiom is sewing, and this is the sort of the heart of the matter, the most interesting one, and for some reason always hard to explain clearly, but I'll try. So suppose the boundary of M has 3 components, and G bar is a diffeomorphism between 2 of them. So here's the boundary of M, and I'm going to orient these 2 components compatibly with the outgoing normal, and this one with the incoming normal. And then I'm going to have a diffeomorphism that maps this boundary component to that boundary component. And so I glue the manifold along that diffeomorphism. That's one of my assumptions of properties in my manifold category. So if this is a manifold with a principal bundle, and we have a principal bundle automorphism from this to that, we can glue. So, and if we have field phi here such that the boundary data agrees here, we can also part of the axioms are that say that we can glue the field. So we want to relate the action for this unglued manifold to the action for the glued or sewn manifold. Okay? So so here's the picture. So the action for the glued manifold should be obtained from the action for the unglued manifold by this kind of operation of trace. So in terms of the picture, if I have the glued manifold and I take its action, I just get an element of the line bundle associated with the one remaining boundary component at the value of the boundary data along that boundary component. Whereas if I start with the unglued manifold and I take its action, well, its action by the properties under disjoint union and orientation reversal is just an element of the tensor product of the line bundles for the data here, here, and here. And this one has a dual because it's got the opposite orientation. So we can just identify that with homomorphisms from this line bundle for sigma 1 to the line bundle of sigma 2 tensored with things in the line bundle for sigma 3. And then if we use the action of the diffeomorphism element G bar acting on the line bundle, that's part of the data, then we can compose and map this line bundle at sigma for sigma 2 to the line bundle at sigma 1. And then we can just take a trace of this homomorphism from a space to itself. And the axiom is that these two should agree. So I don't know how to explain it more. I'll just let you look at it for a couple seconds.
This is also just a line bundleization of the sphere.
This is a line bundleization. So as I said, this is just a TIA. It's just a line bundleization of it. He used vector spaces. I'm using line bundles. Right. And I'm just saying it in a way that happens to be convenient for my purposes, but it's just what he did. So the next axiom is the one that characterizes this as a classical theory. Makes it different from what a TIA has significantly. And that's the axiom of locality, which is that the space of fields and the space of Cauchy data should be spaces of sections of a bundle, that this projection map should be a differential operator at the boundary. There's some surjectivity condition I won't get into. And then we take as an axiom that the covariant derivative of the section should have this form of being given by an integral of this local object in phi. So the variation of s with respect to phi at the point x is a function of phi and its derivatives at x. So that's the locality condition. So that's what characterizes this as a classical theory. And this condition delta s delta phi equals 0 is the equation of motion. Okay, so so just from this I could go on and say, well, what are the properties of this space of solutions to this? And it automatically inherits all sorts of geometric structure, which is sort of a modern newfangled version of doing things like Noether's theorem on manifolds with boundary, where the conserved objects are not just numbers, but line bundles with group actions, and so forth. So what for time, I won't belabor that. So let me just note one example. Sorry about the smudges of this axiom. So for example, if we have a manifold with an incoming boundary component and an outgoing boundary component, then its action is in the line bundle for the full boundary at the boundary data on both places. So we just spell that out. It's the dual of the incoming plus the outcoming pi phi. So this goes to tensor product. So this goes to homomorphism. Okay? We already did fancier when we stated the gluing axiom. And in particular, if the manifold is closed, then the action belongs to the line bundle associated to the empty set, which is just a copy of the complex numbers. That's the consequences of the disjoint union action. It has to be the identity space under tensor product. So that you get a U1 valued action for closed manifolds. So in fact, that's the starting point for the Chern-Simons action. We have this U1 valued action associated to closed manifolds. And what we'd like to do is reconstruct the rest of the theory for manifolds with boundary. Okay? So before I start to do that, let me just, in a way, I'm doing something sort of more foundational, so I can try to be a little more self-contained, hopefully. So the example is, let's look at the 0 plus 1 dimensional generalized Lagrangian field theory. In other words, a theory of mechanics, for Hamiltonian mechanics. And now I look at Hamiltonian mechanics for a given arbitrary symplectic manifold with some Hamiltonian function h. So if the symplectic manifold was just flat R2n, maybe some of you would recognize Hamilton's action principle is that the variation of this expression integral pq dot minus hdt equals 0 is equivalent to Hamilton's equations of motion. Now what we'd like to do is say, what do we need given this data to find an action principle which will have that equation of motion? Well, so what we need is a line bundle, which I'll call L plus, over our symplectic manifold to be a Hermitian line bundle with connection with curvature minus I omega. So that's what the geometric quantization people call a pre-quantum line bundle. But what I'm saying is the pre-quantum line bundle comes for you as part of the classical theory. Okay? I'm saying, people knew this, but so then the definition of the theory is A of a point is just equal, so the Cauchy data associated to the zero-dimensional manifold of a point, the line bundled associated to the oriented zero-dimensional manifold, which is a point with plus orientation, is L plus, and the line bundle for the point with minus orientation is then therefore the dual of that. The space of fields is just the paths. It projects to the boundary data by just taking the values at the boundary. And then I take the action for a path from time t0 to t1 to just be the holonomy of the path times this e to the minus integral I times h. So that's this second part is just the piece in Hamilton's action principle. The first part, the holonomy, is what generalizes this pq dot. And so this belongs to the homomorphisms from the line bundle at the incoming point to the final point, which is just where it's supposed to belong. And if you look at the covariant derivative of this action using the connection on the line bundle, we get this expression here, the symplectic pairing between the variation in the field phi and this phi dot minus the Hamiltonian flow.
So E doesn't make the path-ordered exponential.
This is the path-ordered exponential or right. It's a path-ordered exponential or parallel transport in math terminology. Okay, so that's sort of the example that says even to do something as elementary as Hamiltonian mechanics with an action principle, we should introduce these line bundles. Okay, so now I need to start the reconstruction. I want, so for the Chern-Simons case, we're given an invariant for closed manifolds. Can we reconstruct the rest? And the answer is yes, as long as we have a certain consistency condition on the classical invariant for closed manifolds. So the generalized Lagrangian field theory is equivalent to specification of the fields in the Cauchy data plus an action on closed manifolds which satisfies certain consistency conditions. So we can break the theorem up into two parts. Suppose we're given all the data of the generalized Lagrangian field theory except for stuff to do with the connection. So then we have to replace the locality of the action by this statement that instead of using a covariant derivative, we should use an ordinary variation. And we'll do an ordinary variation that doesn't move the boundary data. So it's not changing which line of the line bundle you're in. So you can just use ordinary derivative. So if that's true, then there exists a unique connection. So you can reconstruct the connection just given the stuff other than the connection and locality. And the idea of the proof, which I won't belabor, is just what we did before in the Lagrangian field theory case. Under an arbitrary variation of phi, the action varies by this bulk term plus some boundary term. And we just take the connection one form to be that boundary term. Then you just have to verify it has the properties you need it to. So Now, so the second half of the sort of reconstruction theorem is, suppose we're given the data, Cauchy data fields, the boundary map, as in the definition, and we're given the action only for the closed manifolds, which is diffeomorphism invariant, has a local equation of motion, and now we need to add these consistency conditions. So the first consistency condition says that the action of a double should just be 1. So this is a closed manifold, so the action should be a number, unit complex number. I'm saying it should be 1. By double, I just mean we glue a manifold with its orientation reversed together. Okay? So that's a property we must have if it's going to come from a generalized Lagrangian field theory. And then the second one is a little more complicated, that if you have something, a manifold with 4 boundary components, all of which are diffeomorphism, and we glue them together this way or this other way, the action you get should be the same. And that would have to follow from the axioms for generalized Lagrangian field theory just by a property of one-dimensional linear algebra. Okay? So then the theorem is then this data can be extended uniquely up to equivalence to a full generalized Lagrangian field theory. So, and there's some technicality I won't get into about if some of the D manifolds are not a boundary. But we can add a few extra words to say it precisely, but I'll just refrain. So the proof generalizes the construction of line bundles with connection and group action from a consistent collection of equivariant holonomies. I mean, so suppose you're given some manifold and you look at a sort of an equivariant path, which just means you have a path in the a group action path in the manifold, group action, path in the manifold, group action. And suppose we have a line bundle and we can form the quantities, the trace of, you just take the holonomy, the group action, holonomy, group action, and it just brings you back to the original fiber. You can take the trace. So in fact, just knowing this allows you to uniquely reconstruct the line bundle with connection and group action from the data. And any such data will come from a line bundle if it satisfies the simple analog of the consistency relation before. So if you wanted, I could spell it out. It's not too difficult. So you could just take the line bundle, the fiber of the line bundle at the point, choose a base point, A naught. Fiber of the line bundle at the point A is just functions, complex valued functions of paths that go from A to A naught, such that if you change from one path to another, the action changes by something you compute using these numbers. Anyway, that's a concrete example you can play with pretty easily. So, okay, so let me finally get on to the Chern-Simons theory. So let me look at Chern-Simons theory in odd dimensions. The case L equals 1 is the case Witten quantized, 3-dimensional. So let's fix a compact Lie group G and fix an element of the 2L plus 2 integral cohomology of the classifying space. And we can let P be the invariant polynomial on the Lie algebra of G associated to the element U may push forward to have real coefficients. So that just means given a principal G bundle, you can pick a classifying map for that bundle to the classifying space BG. And if we pick a connection which has curvature f of a, then the pullback of this cycle RU by the classifying map is supposed to be the cohomology of the invariant polynomial applied to the curvature. Okay, so that's just characteristic classes. So now, again, as I said, my manifolds with additional structure will just be principal bundles over my base compact-oriented manifold, and I'll take this space F to be just the space of connections on the manifold, and pi just to be the restriction map to the boundary. You just take a connection, you're restricted to a connection on the boundary. Diffeomorphisms, as I said before, are just automorphisms of the bundle. And so the simplest case of the Chern-Simons invariant secondary characteristic classes, if this data m bar A, so field with bundle and connection, is the boundary of some manifold in one higher dimension, then just the action be e to the 2 pi integral of f over n, and this won't depend on the choice of n and b. So so if we want to look at the action for a closed manifold more generally that's not a boundary, well, it's easier to picture if we start by taking manifolds in dimension 3, which is the case which most Hay was made of. So we can, by a cobordism theory argument, you can pick an integer n so that n copies of the manifold is a boundary. So then you can pick a classifying map for this bounding manifold. You can pick a chain representing u, and then we can take the action to be e to the is, where s is valued in r mod 2 pi z, which is 2 pi over n. And now we have to divide through by n, because we took n copies, and we have the same integral of p of f. And then we have to subtract away this sort of discrete stuff, pairing the chain and the push forward by the classifying map of the sort of a top cycle representing the fundamental class of n. Push that forward into a chain in BG. So, okay. So if we want to go beyond the case of d equals 3, and also if we want to have the flexibility that we need to prove the consistency conditions so that we can reconstruct a full theory, then we just will replace this bounding for manifold just already by a singular chain in BG. Okay? And this is essentially the construction of Chigger and Simons in 1985. So the general invariant has the same expression where this isn't a bounding manifold, but it's just a bounding chain here in BG. What's that? Yeah, I was surprised. I have a copy of the paper. It says 85. It's probably older. When was it?
It was written in 73.
It was.
Just
took a long time.
Jeff took a very long time to send it to the publisher. He kept meaning to, and he lost it.
I see. I was surprised that it was 85, I have to say, but 73. Maybe I should go back and fix that, and I think it'll take a while. So this has the properties that the difference between the action, if you just change the connection from A to A prime, it's just now you can always pick some bounding manifold like just M cross an interval, such that the boundary is equal to well, I should say M bar A union M bar A prime, and then the difference here is automatically the integral over n of this. And then that implies that the variation in the action is a local expression, integral over m, and then we just take the derivative of the invariant polynomial applied to f of a, wedge delta a. So the variation is just this. So that's local as we need. And then just following the construction, the general reconstruction argument before, if we pick a base point, and there's a way to do it without picking a base point, but if we pick a base point, then it naturally determines a trivialization of the line bundle where the connection 1 form just looks like this. It's an integral over time. This expression that involves a, the difference between a and the base point, and the second derivative of the invariant polynomial. And then, actually, this is just I ended up writing I kind of got into this whole production in my thesis. I just needed this part to finish the construction of the Hilbert space. I needed an action of the diffeomorphism group. So here we get that action of the diffeomorphism group unwinding the reconstruction construction. In this trivialization, the action from here to here is just multiplication by this factor of automorphy, which is just the action, the Chern-Simons invariant, for the manifold, which is you take sigma cross an interval to A, sigma cross an interval from R of A to A naught, and to the natural trivialization, we just make this a linear interpolation. We glue these together with the diffeomorphism, and then we glue these together with the identity map. We take the action for that. That's the factor of automorphy. But to prove its properties, we need to use the fact that we work with chains in the classifying space, so we had the flexibility to do the construction. So, okay, so in a way this is pretty down to earth, and I just want to say that sort of homological algebra machinery is very natural and goes through to quite a bit of generality that we need in various constructions with this gauge-Wess-Amino action. So, so now I'll spell out about these differential characters, what I mean by equivariant differential characters. Okay, so let me fix a non-negative integer and fix group G acting on a manifold X. So for the Chern-Simons case, X is a point. And then I can introduce the homotopy quotient of X, which is just the bundle associated to the universal bundle for the group G with fiber X. And so the equivariant homology of X is just the homology of the homotopy quotient. But in order to do the construction, it's convenient to introduce another chain complex, which also computes the homology of the homotopy quotient. And I'll just say it's chains with connection. That's what we needed in order to define the invariants before. I said this whole data, instead of a bounding manifold with connection, let me take a bounding chain, and that had to have connection. So I can put connections on the chains, but I can do that for free. That's a flabby thing to do. It doesn't change the homology. So, and so then I'll introduce the Cartan model for equivariant cohomology. And so it's just a generalization of the de Rham complex of X, which also adds in invariant polynomials on the group. And so it's called G equivariant differential forms on X. So now that I've introduced these connection on the chains, we have a pairing between this chain complex computing equivariant cohomology, this cochain complex, which in the case when G is compact computes equivariant cohomology. But in any case, in general, we have this pairing, which I can kind of schematically denote. If I have K is a well, that's really a kappa is a chain in X, and the bar means it's also equipped with a connection A. And P is a differential form on X tensored with symmetric polynomials. Then we can just generalize what we did before, integrating over the manifold P of f of A by integrating over the chain P of the symmetric polynomial, and then we sort of use the sort of universal section to pull that back and get the form here. Okay, so and this is a pairing on complexes, and so it descends to a map from the cohomology of this complex to the equivariant cohomology, which, as I said before, is an isomorphism for G compact. If G is not compact, it's not an isomorphism, but we'll still find it very useful. So, okay, so now we just follow in footsteps, and hopefully we'll be rich soon then. So I'm going to define the equivariant, so I'm just going to equivariantize their definition of Chern-Simons and define the equivariant differential characters, so it's valued in R mod Z, to be the set of homomorphisms from cycles in this equivariant chain complex with connections to R mod Z, such that F acting on F composed with boundary is in this Cartan model, the equivariant differential forms. So sort of souping up the argument in Chern-Simons, this is characterized very well. I mean, it's a very kind of abstract definition, but there's several exact sequences that characterize it quite well. And so I'll just take the sort of most powerful one. So there's a map from equivariant differential characters to this space sort of equivariant version of the space introduced by Chern-simons, which is just the space of pairs Pu, where P is an equivariant differential form and U is in equivariant cohomology with integral coefficients, such that the realization of this is equal to the image of that under that homomorphism to cohomology. So for the case where X is a point, the Chern-simons case we discussed already, and where G is compact and K is odd, what we really did there before was we noticed that just by some calculating the cohomology of the classifying space, this is 0. I mean, this was noticed in Chern-simons. And so then we have this map here to equivariant cohomology, equivariant differential characters of a point, and then that maps to Rj k plus 1 of x. And if G is compact, this P is determined once you know U, as we said before. And so there's one of these equivariant differential characters for each element of hk plus 1. Okay. So now I can state sort of the final reconstruction theorem. So let's consider generalized Lagrangian field theories defined on manifolds with a principal G bundle and with the space of fields just being connections crossed a section of the bundle associated to the principal bundle with fiber X. And similarly for the Cauchy data. Then let f g d plus 1 of x to be the set of isomorphism classes of generalized Lagrangian field theories with this data. And then the theorem is there is an abelian group homomorphism. This gets a group structure under tensor product. So there's a abelian group homomorphism, which is in fact injective from these equivariant differential characters to generalized Lagrangian field theories. By the way, these equivariant differential characters actually form a ring, so I'm not using the ring structure here at all. And so, in fact, this homomorphism is determined by the reconstruction theorem before by its value on a closed manifold. And so the value on the closed manifold is, so suppose we're given a differential character, we're given this closed manifold, we just apply the differential character as the chain we get using a classifying map and pushing forward a chain representing the fundamental class of the manifold, and equip that chain with the connection that we have. So that's the definition, and then sort of it's an exercise. You can check the properties. But now you only need to check the consistency conditions. It's sort of a homological algebra argument. So okay, that's. I'm not. Actually, I'm a little ahead of schedule, but I'm not planning the time to explain lots of examples. But let me just do the simplest one, which we already started with, which is the case of ordinary mechanics. So D is equal to 0. And the fact is that these one-dimensional equivariant differential characters classifies Hermitian line bundles over the space X, which are equipped with a connection and a group action on the line bundle, preserving the connection. And so this, in fact, map, this inclusion, expresses these differential characters as a subgroup of the space of field theories, and it just corresponds exactly to the field theory with Hamiltonian equal to 0. In other words, the top classical topological theories. Okay. So, any questions about that? Okay. Well, no, okay. I'm not going to go on just because I have a little more time than I thought. So I left myself breathing room, which was just to make this very vague statement. And I'll leave it at that so people can rest. But so this is really part of a program, you could say, of sort of, well, I don't know, maybe it's out of fashion, sort of Bourbaki for this kind of field theory, where we can relate various functors from the category of manifolds with additional data. like those manifolds with principal bundles, to a category which I could define of vector spaces with pullbacks and sections. And these categories have analogous operations. And all of these things are such type of functors. Generalized Lagrangian field theory, I explained. Topological quantum field theory, Tia explained. A general quantum field theory, you got to worry because the things are infinite dimensional, and that's what worked on for. I think that was one of the things that made it difficult and drags on. But also the space of classical solutions of the generalized Lagrangian field theory, as I alluded to, is just a functor of just this kind. And this is sort of a more specific program is can you explain how to make renormalized perturbation theory for the generalized Lagrangian field theory as a functor within this framework? I think you can do that. At least.
The whole point of all this is to get away from perturbated particles.
Well, so in the Chern-simons case, we're very happy because he constructed this functor. And he started with this, and he didn't sort of do a natural transformation of functors. He sort of used an oracular transformation and produced that. But in the general case, sometimes perturbation theory is all we have a handle on. And we might want to use it to get insights about this. So for a lot of these string theory arguments, you're really doing string perturbation theory. And you're getting a lot of structure out of that. Like in Yao's talk last time, a lot of that can be viewed as string perturbation theory. A lot of these duality arguments are saying we can relate string perturbation theory here to non-perturbative string theory over there, but which is perturbative in another parameter. So it's a bummer that we can't always get beyond perturbation theory, but on the other hand, it's pretty happy that it's so useful, right? And the hope, though, is if we understood this more properly, it would help us kind of to bootstrap. But I wish I had a better answer for that. Okay, so I'll stop there.